Hey, Vlad here, devinsidey.com. Welcome to another video. In the previous video, we learned about the point-free style and we went all the way up to Kleisli composition and saw our first monads appear. In this video, we will switch back to the regular style, derive monads from that angle, learn about their laws, and generally speaking, play with them a bit more. Alright, let's get right to it. As always, we're in the Ubuntu virtual machine and we're running Sublime Text fully maximized with a plugin called Terminus, which emulates the entire terminal for us, which we use to run SBT, which we use to rerun the main every time we save the file. So this is exactly where we left off. We had this Kleisli composition and we were running the point-free program. So today we're going to switch to running the regular program like this. And the point program, I'm going to switch to it over here, going to create a bit more space. All right, let's see what we had there. So we had this create description, which was kind of big because we were creating only one IO. So the goal today is going to be to do the same thing as we did with Kleisli composition. We're going to separate this one IO into many small IOs, and we're going to compose them together, and we're going to see how flatMap and monads play into it. A lot of the things in this video are actually going to feel like a deja vu from the previous video. So the first thing that we're going to do is we're going to clone the display line, and we're going to create the display Kleisli version. Okay, display Kleisli, which doesn't return a unit. It returns instead IO of unit, like this. Okay, so instead of just printing the input, it will actually go here and say IO dot create like this. Now I have one curly brace too much. There we go, like this. Let's see if it compiles. It does. All right, so let's try to use display Kleisli. So we're going to go here, display. Boom. Okay, and the same as in the previous video, we got unlucky because it compiled, but the behavior of the program changed. Before fixing that, let's go and do the same thing with prompt. So I'm gonna duplicate prompt, gonna go up like this. Okay, so because prompt is going to be, first of all, it's going to be called prompt Kleisli like this, because it doesn't produce just a string, it produces IO of string. We actually don't need those parentheses because now we're back in the referentially transparent world. Okay, so all we need to do is to go here and say IO create 5. Okay, right, like this. Let's save it. Let's also indent one line like this. Let's go up to prompt Kleisli. So now if we put prompt Kleisli here, obviously it's not going to compile because it doesn't return a string. Okay, so I mean, let me show you. Okay, so now it doesn't compile. Okay, so if we wanted to fix that, we will need to do the following. As of right now, we don't really know how to compose them, so I'm just going to say unsafe run over here. Okay, just so that it compiles. So we're creating an IO of string, but then we're running it right away. But you know, this is not ideal, but this is the only way we need to. We know how to do this. So we're going to do the same thing with the others as well. So what I'm going to do is I'm going to do this a bit more explicitly. So I'm going to say that this is the first IO, which is the IO of unit. Okay, and over here we're going to go and say first IO dot unsafe run. And I forgot I brace here. Okay, so now if I save this, we should at least see the first line. So now I'm going to do the same thing with the others. So I'm going to go here. I'm going to say this is the second IO, which is also IO of unit, like this, right? And I'm going to duplicate this line. Just going to go here. I'm going to say second IO unsafe run like this. I'm going to do the same thing with prompt Kleisli. So I'm going to cut it out and I'm going to say third IO. Okay, and I'm going to create the third IO over here. So I'm going to say third IO, which is IO of string, equals, it's the same as prompt Kleisli. Okay, I'm going to press enter over here. Now I'm going to go down over here. Let me also save the files occasionally. Okay, so now we're going to have the fourth IO. In fact, you know what? I'm going to call it fifth IO because we're going to have a fourth IO a bit later. Okay, so this is going to be the fifth IO, which is an IO of unit like this. I keep missing the right brace. Okay, so we're going to have fifth IO dot unsafe run, and this one is going to be the sixth IO like this, IO of unit like this. Hit it this time. Okay, 6 IO dot unsafe run like this. Okay, let's save. Cool. All right, so as I already said, we're not actually composing anything. We're just creating this one gigantic IO, and then over here we're creating a bunch of small IOs, but then we're running them right away, so there's actually no point in creating them. Okay, so what we need to do is we need to start composing them. Now, in the previous video, the reason for creating more Kleisli arrows was so that I have an example to show you of Kleisli composition, right? But in this example, we have sort of like a better, more practical goal, because even, you know, by wrapping the entire thing into one IO, we're creating an illusion of a functional program, but there's nothing functional about it. If we look inside, we're still side effecting like a boss. Okay, so this is clearly not the goal, and this is where we're gonna use composition and then later monads to see how we can reason over here inside of create description also in a functional way, which is exactly what we want. All right, so how are we going to do this? Before we're going to start, I'm going to show you, if we go back to point 3, and I'm going to show you the Kleisli composition. Remember, we were composing 2 Kleisli arrows and we were producing another Kleisli arrow. So what we basically need to do is sort of manually do the same thing over here. So the goal is, if we want to compose like this one and this one, we need to wrap both of them into its own IO, and then inside of that we can call unsafe runs, right? Because inside of it, it's fine to have side effects, right? So this is what we're going to do, and we're going to do this step by step. The first step is going to be to copy this part. I'm going to paste it over here, right? So this is going to be io.create, and now everything, the rest is going to be inside. Notice there's name shadowing, which is going to help us. Okay, so now what we can do is we have access to the first IO, so we can just bring it down, right? Because it's okay to call unsafe run inside of IO. Okay, and now because we don't want the behavior to change, we also want to go down over here, and we need to evaluate the second IO. Right, so if I don't have this line, then we basically ruined one of the steps, right? We're not running this anymore, okay? But if we're running that, then the behavior remains the same. And notice that if I collapse this, then it doesn't feel like we're running first IO, right? Because first IO is being run inside of the second IO, which is fine. So we're not just creating an IO over here and calling unsafe run on it right away, right? Because that would be a side effect. On the other hand, over here, because it's inside of IO create, it's fine to run it. Okay, so now we're going to go and through all the others and do the same thing. Okay, so I'm going to copy that. For example, this is the third IO. I'm going to paste it over here. I'm going to say this is going to be IO create, right? Open the brace over here like this. Close it over here like that. Okay. In fact, let me also open this one so that you can have something to compare with. Let me also create more space like that. Okay, so that it starts looking the same. Okay, so now I'm gonna bring this down the same way as we did before. I'm gonna press enter over here. And now we also need to return an input over here, right? Because we need to produce a string, okay? And at the bottom, we're also going to do this part. Okay? In fact, obviously, it's not only this part, it's actually this part as well, right? So it's the entire line needs to come down, right? And so that I don't have, so that I don't make the same mistake, we will also do something like this over here, right? We're going to say underscore unit, so that you see that there is actually something that's coming back. So I'm going to say that this is the second IO result, and over here I'm going to do the same trick over here. I'm going to say unit equals first IO result. Oh my god, I can't type. First IO result and second IO result, like this. Okay, so we're gonna skip the fourth IO, so to say, right? Because we went straight to the fifth one. Now the next steps that are happening here, there is no IO involved, so we have a choice to make. We could, for example, move it inside of the third IO, and then what the third IO would produce is not going to be the input; it's going to be straight the message. Or we can move it to the fifth IO, or we can wrap in another IO around it, which is going to be a little bit less performant, but I believe it's going to be better for educational reasons. So this is what I'm going to do. So I'm going to go here and I'm going to say that this is going to be the fourth IO, which is also going to be IO string, right? So I'm going to go and I'm going to say IO.create. I'm going to wrap this entire thing into IO create like this. There we go. Okay, so now I'm going to bring this down. I'm going to bring this input down the same as we did before. Now we have access to input over here, but now we need to return the message over here. Message like this, okay, and at the bottom we also need to run it, so we need to duplicate this line basically, sort of, right, like this, and it's going to be fourth IO dot unsafe run. Okay, so if you know a little bit about monads, or at least about full comprehension, this is going to become a map in the future. In fact, because I want to sort of avoid confusion before I introduce map properly, we're going to have another IO inside of this, right? So because this is what we had so far all the time, right? So we're creating this relatively big IO, and inside of it we're evaluating one by calling unsafe run. Then we have some other IO, but in this case we don't have any other IO. Okay, so now I'm going to artificially create it and call unsafe run on it right away. So I'm just going to go over here and I'm going to say val fourth IO. Like I'm looking it up from here. Basically I'm typing the same thing, so it's going to be IO of string, but in this case we don't have it, so we're just going to create it. It's going to be this whole thing, right? So it's going to be that. Okay, but now at the bottom I'm going to do the same thing as I did over here, right? So I'm basically I just created it just so that it can run unsafe run on it right away, which is usually not what you want to do, but for this educational purpose I just want to make it look exactly like these ones. Okay, so there we go. I'm going to save the file, and I made a mistake somewhere. Let's see. Probably I forgot to return message over here. And there we go. Okay, so now it looks the same. And let's see, the next one is going to be the fifth IO. Okay, it's going to be this one. Same pattern as before. We copy this line. We have io.create, closing it over here, moving it to the right, bringing this one down like this. Okay, and returning the same line over here. Clone it like this, bring it down. Let's see if I made a mistake. No, I didn't. And also because I wanna make them look exactly the same as the others, I'm also gonna do this. So this is going to be the second IO result, which is going to be a unit, and we're also returning it. Second IO result, like this. Man, I can't type. Jesus. Okay, there we go. Over here we're already doing this. Okay. Over here, did I forget this? No, over here we're already doing this. Over here I forgot this. Okay, so this is going to be the fifth IO result, which is going to be a unit, and we're also going to return it like this. Okay, and now the only one that is left is the sixth IO. It's like this, so I can do that. io.create. I'm gonna put this like here. All right, so now I can bring this down. Right, I can also do this unit trick, which I probably forgot before. This is the fifth IO result. Okay, this is going to be the sixth IO result, just unit. Okay, and I'm going to return it over here, right? And in the end, we're going to return 6IO dot unsafe run, the same as over here. Okay, so let me save this, and also let me go up to see. Okay, so this was also the fourth IO result, and this was the third IO result, and yeah, second IO result, first IO result. Okay, so now everything is cool. So what I can do now is I can go and collapse all of them like this, like this, like this, and okay, there's a mistake over here. We actually don't need that. Fifth IO, 6 IO. All right, so this is what we have. We have a bunch of IOs, and we're calling unsafe run only once. So now, instead of calling unsafe run, I can just return the IO, and instead of wrapping in the entire thing, we have the composition. Okay, so now instead of having one big IO, we have a lot of small IOs. We compose them together, and we return the last one. And notice that because we're not wrapping the whole thing into an IO, we can't just go and have side effects over here, right? So you can't just do print line high because this print line will be now red. This is not what we want. So now we have sort of like, you know, even though the compiler is not ensuring that, we still have like a little bit of sort of guarantee. Like you could do this with automated tests, but I wanted to go a bit faster here. Now I claim that all of this composition is the same, and in fact we've seen it in the previous video. This is what flatMap will do for us. It will take over this composition. So I'm going to take one of them, for example, the fifth IO, and I'm going to go to our IO over here. I'm going to go to flatMap, and I'm going to create more space like this. So what I'm going to do is I'm going to paste it right under the flatMap so that you can see that it's basically the same thing. So if I paste it over here, and now if I just start creating a method around this, you will see that it will basically become flatMap. So I'm going to call it compose. So I'm going to call it compose. And I'm just going to wrap the entire thing like this, right? Now, in order to make it compile, I need to make things, appear in scope. So first of all, what this will produce is the fifth IO, right? So it creates the fifth IO and returns the fifth IO. So the result is going to be an IO of unit, okay? And now in order to make this compile, it needs the fourth IO. Well, the fourth IO is an IO of string, right? Because when we call unsafe run, it produces a string. So what we need to have over here is we need to have the fourth IO, which is a not a string, it's an IO of string. And the second parameter, and let's create right away, because I already said this will essentially become this flatMap. Okay, so this is the fourth IO, and what else do we have? We have display Kleisli, and display Kleisli, it's a function that takes a string and produces an IO of unit. Okay, so display Kleisli is going to be a function that takes a string and produces an IO of a unit like this, and now I believe it should compile. Right? We're obviously never calling this compose, but this is all that we need to make it compile. So what we can do now is we can say, why should it work only for strings and units? So if we introduce two parameters, A and B, right, the same as we have with flatMap, then everywhere where we say string, it's just going to be an A, and everywhere we say unit, it's just going to be a B, like this. And it still works. Now let's just rename a few things. So instead of saying fourth IO, we're just going to say that this is an IO of A, and therefore it's not a message, it's just an A. Okay, this is not display Kleisli, this is just an A IO B, right? So the result is then IO of B, and then if we're calling IO of B, then we're producing a B. So in the end, we're just producing a B, right? So this entire thing, this fifth IO, is actually just a IO of B, and this is exactly what we need to produce, IO of B. And also now I'm going to inline this because we don't need that, right? Create like this. Now the types don't really help because it just says AA, IOB, IOB, so I'm just going to remove them. Okay, and we don't need that comment anymore, right? IOB like this, and this like that. Okay, so now because it's going to become a flatMap, and in flatMap we use these names, we can also use them as well over there. So this is not an IOA, this is just a CA. I just basically want to finish making it look like flatMap, okay? Because it's exactly flatMap, not similar, not close. It's exactly, okay. So an IO becomes a C, okay. Look, it's exactly the same code. We have IO create over there, which I put over there. We don't need this curly brace over here. We don't need it over here. So I can join these lines now, and I can save. Okay, so now it looks exactly the same as flatMap. So it has been flatMap all along. We have an empty line over there. Okay, cool. So this is now our flatMap, which means that we can use our monad to do this composition for us. So if we go back to the main over here, right? So now we can get the monad. Right, we can say val m equals, which is of type monad of IO, and we're going to use the summoner. Oh, where's our summoner? Summoner of monad. So the monad has the summoner, right? So we can just say, give me the monad of IO. So now that we have this m, let me save it. Okay. Now we can go to the fifth IO, for example. Let me unfold it. Okay. So now I can say val fifth IO of unit equals, and now we have this monad, and now we can call flatMap on it. And what does it need? Well, first it needs the fourth IO, and then it needs a function that can take the message and produce the fifth IO. Well, it's just display Kleisli, right? So we can just put this in. I can comment this whole thing out, right? And there we go. It's exactly the same result. Let me scroll up a little bit. Same result. Okay, nothing red, just this green. Now let me write it a bit more explicitly so that it's just more more visible, because usually what you do is you have curly braces over here, and then you're going to say, okay, message is going to come in, and we're just going to call display Kleisli on the message, right? Because I believe this is a bit more clear if you're not used to functional programming. Okay, so now I can remove all of that. Okay, and this as well, right? So this is classic composition, right? This is what flatMap is doing. It is composing, in this case, IOs. So let's do this with the others. So if we open this one up, I'm actually going to just duplicate this one. Okay, I'm going to call it 6IO, and what it needs the fifth IO. And what does it need? Well, it needs a unit, right? Unit like this, the underscore. And what does it do with it? Well, it just does display Kleisli hyphens. Okay, so let's just do that, paste it over here. Let's remove the 6IO like this. Okay, let's see, same result. Cool. Let's go to the others. Let's skip the fourth IO for now. Actually, let's do the third IO first. Okay, so I'm gonna duplicate that line. I'm gonna bring it up like this. Okay, so now this is going to be the third IO, and what does it need? Well, it needs the second IO, and what does it do? Okay, the underscore comes in. What does it do with the underscore? Well, it just does prompt Kleisli. Okay, so it's just this. Okay, so this is the same thing as the third IO. Let me comment this out. Okay, I made a mistake. What did I do? Oh, it's obviously not an IO of unit. It's an IO of string. Okay, string. There we go. Okay, so the same thing. We see the green lines, and in fact, I should create more space, and I want to see what we're writing. In fact, you know what? I'm going to try to destroy the pane that is down there. Okay, that didn't really work. Okay, let me fix that. So I want to have ZSH over there. I don't really want to have the interpreter. I don't want to have the interpreter open anyway, because we're going to stick to the point program. Okay, so we have ZSH over there. I'm going to bring down the point program. We can actually, do we need the point? I'm going to leave it. Okay, so at the top we have our functional library. Okay, so this way we have a bit more space. Let me switch back to the paint program to the point program. Okay, so now I can remove the third IO. Now we can go and do the same thing with the second IO. Okay, by copying this line, bringing it down, and bringing it up. This way I'm not going to make the mistake. So this is going to be an IO of unit. What does it need? Well, it needs the first IO. There's an underscore. What does it do with it? Well, it does display Kleisli question. Okay, so let's just do that. Remove that. All right. Do we see the same thing? Yes, we see the same thing. Okay, let me actually save it. Okay, there we go. And yeah, that's all we have. So now we're using Monads to compose. Let's actually do the same thing with fourth IO now. So I'm just going to copy this line, for example, and whoops, like this. So this is going to become the fourth IO. What does it need? It needs the third IO, and third IO gives us an input. So we have an input over here, right? And what do we have here? Okay, it needs the IO create. So it needs this thing over there, right? So this is exactly what it needs, like this. Let's save it. Fourth IO is twice now, so we're just going to remove that like this, right? And as I said in the beginning, like if you already know a little bit about Monads, this is going to become a map in the future, and then we won't need to do IO create over here. All right, so what we have now is exactly the same thing as we had before, but now the composition is being done for us with flatMap. Okay, so but the structure remains exactly the same. Now it is common to use the object-oriented or the infix notation for this. So we're going to have a tiny helper over here. So we have the infix notation for point free, we have the infix notation for point free Kleisli, and now we're going to have yet another one. So we're going to go here and we're going to say this is going to be an implicit final class, and I'm going to call this infix notation for, I'm going to call it for higher kinds, because it's not going to be just for monads, and it's going to be for some C, okay, and for some A, and there's going to be a private val CA, which is a CA, which is why we have those parameters. It extends any val, okay? And what it's going to do, it's going to have the flatMap, right? So it's basically exactly the same pattern as above, right? So the flatMap is going to have a B over here. Now we're going to have a CB, which is an A to CB. And now we're going to say, okay, if there's a monad for it, so if you're going to say implicit M, which is a monad of C, then we can produce a CB. And how are we going to do this? The same as above. We're just going to use the monad. We're going to call flatMap. We're going to pass in CA, and we're going to pass in ACB, and now let's see if I made any typos. No, I didn't. Cool. Let's also have the same syntax for, we're not going to use it, but still, we're sort of creating a functional library here. So I'm just going to clone that. I'm going to call this bind. And I'm going to call this greater equals the same as in Haskell, okay, like this. So now what it allows us to do is basically to say if there is a monad for IO in this case, then instead of doing m.flatMap and then passing it, we can just call it right away like this. Okay, so we can do first IO.flatMap. This is what this thing is doing. Okay, so like this. Okay, so let me remove the parentheses. Let me do the same thing with the others. So I can just cut it out, put it over there, remove the parentheses, do the same thing over here. Third IO goes over here, remove the parentheses. fourth IO over here, remove the parentheses, fifth IO over here, remove the parentheses. Let's actually create more space over here, like that. Okay. Oh, and that's actually already it. So now we don't actually even see that monads are involved, right? So we can just remove this line because it's being resolved implicitly. It's being just summoned, right? So and I believe that this object-oriented version also sometimes causes a bit of confusion because people see flatMap and they don't even know that it relates to monads. Now it's a different discussion if it's important to know, but I believe it is because there's no, there's nothing mysterious about it. The next thing that we can do is we can just inline on the vals. I mean, if you look at first IO, we're just using it over here, right? So we can just take that, put that over here, remove the first IO. Okay, and now second IO, well, we only use it over there. So we can take that and put it over there, right? And remove the second IO. Okay, so I'm just gonna go and do this for the others, and then I'm gonna indent the code a bit differently. So this is gonna be the third IO, so we can just cut it out, put it where the third IO is, remove the fourth IO. Now the whole thing over here, I'm just gonna cut it out, put it where the fourth IO is, remove that. It's all mechanical. I know it looks ugly, but it's gonna make sense in just a few minutes. Cut that out. This is the 6 IO. You don't need this val over here. And what are we doing? We're just returning it like this. Okay, so let me go up and let's see what clariform is going to do with it. And by the way, we don't need this curly brace anymore, actually, like this, because now the whole thing is just one expression. So let me just save it and let's see what clariform is going to do. And in fact, it doesn't look so bad. Okay, so we have display Kleisli. We're calling flatMap, flatMap again, flatMap again, flatMap again. Let me collapse this one a little bit. And what else can I collapse? Actually, nothing. So basically, we have this chain of flat maps. And I did it like this so that I can show you the monad laws, because the monad laws are very, very important. And this example is going to show you why. Before we do the laws, let me actually remind you that I said it in the previous video. What we have now is actually not a monad. It's actually just the part of the monad. It's the major part. But still, the laws that come with this part there's only one law. It's called the associativity law. But a monad technically has two more laws, which we're going to see once we actually finish writing the monad. Okay, so this associativity law, I'm gonna write it all out and then I'm gonna explain it. So associativity law. So this is going to be pseudocode, right? So it's going to compile, but it's not actually going to do what it's supposed to do, right? So it basically says that if you have some type, like absolutely any type that has a monad. Any type that has a monad for some A, okay? So in our case, it's going to be IO of A, okay? So I'm just going to show you that it compiles, okay? In fact, we're not gonna run anything. We're just going to compile, okay? So because these laws, they have to work for absolutely any type that has a monad. Basically, they have to work for any monad, okay? So now let's say that our any type is going to be an integer, just an example, and we're going to have some value of this type. Okay, which is an integer, so it's just going to be 5, right? So all of this is just example, right? So this law is going to work for all the monads, for all the types, for all the values. Like this is the point, for all. And by the way, this is why I came up with the idea that this is a good time for me to create the monad videos, because right before I created the monad series, I created the video with a crash course for property-based testing, and property-based testing is ideal for this, right? So we can just generate a bunch of integers, throw them in here, and they will gonna test these laws. Now, obviously, they're not gonna prove these laws like in the mathematical sense, but it's better than nothing, or it's better than coming up with examples on our own. So now let's say that we have an IO, okay? So this is anything that has a monad of any type, right? Which is just a type alias, right? We know that this is just an integer, okay? So we're gonna have IO.create any value. So this is our IO. And now if we have a function f that goes from any type, right? From here, it goes to some other IO, right? So it's still IO, so it's still the same monad, right? It has to be in the same monad, but for some other type, for example, string, okay? It's going to be, okay, A comes in, IO create, A dot to string comes out, okay? And we have a function called G, which goes from string, right? So from here, so we're going like from here to here, and then from here to something else. Let's say anything that has a monad, and now the type can be different, right? So it has to be, it has to be in the same monad, right? But the type obviously inside can change. Okay, so this one looks like this. A comes in, IO dot create print line A, right? So being very, very explicit. Let's see if I made any mistakes. No, I didn't. Okay, so now the associativity law, it says that if you call flatMap with an F, and then whatever comes out, you call flatMap again, and now with G, then it should be the same thing. And notice that this is pseudocode, right? So this is equality, and equality can't just automatically test for side effects, right? Then this is going to be the same thing as IO dot flatMap, and A comes in, and we're going to apply A to F, okay? And then on that, we're going to call flatMap G. Okay, like this. And if I write it in different terms, maybe it's going to become a bit more clear what is happening here. What is happening here is basically Kleisli composition, right? So it says that if we chain these like this, then over here it's going to be the same thing as if we were composing Kleisli arrows, right? Whoops, like this. Right, so it's exactly the same code, right? We have this Kleisli composition. This is exactly why I did it, because now it basically says, okay, you're either chaining the flat maps or you're chaining the methods. A bit later in the video, we're also going to learn about map. So map is going to look like this. If we have a function f1 which goes from any type directly to string, so this one went to IO of string, this one goes straight to string, right? So it basically just goes, okay, A comes in, and then we do A to string right away, and we're going to have G1, which now goes from string to directly to unit, right? So A comes in, and it's just this print line of A, okay? Then the similar laws are going to apply, right? So it's not going to compile now because we don't have map yet, but we're going to have it in a few minutes, right? So now if I replace map everywhere here, okay, then over here it's going to be the regular composition, right? And obviously this code is not going to work because this is actually like this. So it's going to be F1 applied to A, and then it's going to be stuck into the G1, right? So this is the regular composition. By the way, this is F1, G1, F1, G1, okay? So we have the monad stuff, right? The Kleisli composition, and we have the regular stuff, the regular composition. Now this is not going to compile because we don't have map yet, but I'm going to comment it out, and once we're going to have map, it's going to compile, okay? Like this. Okay, now usually the associativity law is explained in terms of parentheses, right? So if you have integers, right? So if you have an integer, which is 1, and we have B and C, we have a 2 and a 3, then usually the way it's explained is it says, okay, if we have A plus B and then plus C, then it's going to be the same thing as A plus B plus C. So this is how the associativity law is usually explained. It says, okay, you can just put the parentheses wherever you want. Let me save it. Okay, but I'm showing you this to show you a different explanation because we're in Scala and plus is just a method. So basically what this says is that if you have A dot plus B like this, okay, and then you chain them like this, right? So if I have a, oh man, come on, let me do it like this, dot plus C, right? So I wrote exactly the same code. I mean, there are parentheses over here, right? But we can ignore the parentheses for now because we have the dot. If we have the dot, we don't need the parentheses. Then it should be the same thing as the same thing that is on the right. We have A dot plus, and I'm going to open the brace over here, and I'm going to have B dot plus C. Okay, so basically it says that the chaining things is the same as nesting things, or in other terms, it doesn't matter how you nest things. Whoops, what's up? What happened? Oh yeah, the equality. It doesn't like the equality because it's over there because of the semicolon inference, okay? So basically it says it doesn't matter how you nest things, right? If they can be chained, then they can be also nested. And this is the thing that that we're going to use now with flat maps. So we can go to our flat maps because this is what we have. We have the chain of flat maps, and we want to replace it with a nesting of flat maps. So I can, for example, take the last one. We can actually switch back to running now, like this. So I can take the last flat map, I can cut it out, and I can call it on over here, right? So is it better to call it like this or like that? Maybe it's better like this, okay? So this is going to be exactly the same code. And now I can do this one, right? So instead of having a chain, I can call it on this one. And the same thing with this one. Instead of having the chain, I can call it over here, right? And the last one is over here. Is it the last one? I'm not sure. Okay, I can just call it over here. All right, so now we have this nesting of flat maps. If I collapse this one, no, that's too much. If I collapse this one, then you will see, okay, we have something flat map, and then inside of it, flat map, inside of it, flat map, inside of it, flat map, inside of it, flat map. And if you've seen my video about full comprehension, this is like the typical smell of monadic design. If you have this nesting, if you have this callback hell, which is, you know, actually something that monads solve. So what we're going to do now is we're just going to copy that. Okay, I'm going to now comment it out, and I'm going to start typing it over here with a for comprehension now, right? So I'm going to have create description, args come in, which is an array of string, and IO of unit comes out, and it equals, and now we can just say for, and in the end we're going to say yield this, right? So and now inside of it we can just take this underscore, and we can say, okay, it comes from display Kleisli hyphens, okay, like this. And then the next underscore, it comes from display Kleisli question, like this. And then the input, it comes from Kleisli. And then the next thing is we need to unfold it like this. This message over here, this message over here, right? Let's put it down like this. This message over here, it comes from this, like that. Let me copy that. Let me paste this over here. Let me obviously remove this, like that. And Scalariform is going to fix all of this later, but yeah. All right, so we have the message, and now the next flatMap has this underscore, which is over here, this underscore, and it comes from this over here. And the last one is this underscore, and it comes from display Kleisli hyphens, like this one. Okay, so now if I save this, it's actually not going to work because the way the for comprehensions are coded, they actually need a map. So what I'm going to do now is I'm going to comment this out because of this last thing. The last arrow is not going to be converted into a flat map. It's going to be converted into map. So what I'm going to do over here, I'm going to comment this out. I'm going to go back to our original problem, which was over here, which compiles now. So when the for comprehension is done, what it does in the end is this. So it does map, and then the thing comes in, and the unit comes out, right? But this is obviously not going to compile with the same error message. It's going to say, hey, map is not defined. In fact, if I scroll up a little bit, this is what it was doing. Over here, it was saying, hold up, you don't see it here. Value map is not a member of IO of unit, right? It was happening in the last line. So now we have exactly the same problem. So what I'm going to do now is I'm going to comment this out real quick, and we're going to go and create map. So we're going to go to our monad over there, okay? And we're going to say that a monad, it doesn't only need flat map, it also needs map. So I'm just going to duplicate this line, and I'm going to have it above, okay? So all we need to do is we need to call it map, and we need to say that over here it doesn't need a C of B, it just needs a B, but the rest is going to stay exactly the same. Okay, so now if I'm going to save this, nothing's going to compile because IO doesn't implement this. So let me go to IO, and I'm going to duplicate that, and I'm going to do that over here. Okay, so let's see, the same as before. So what do we have? Well, we have CA and we have ACB. So what we want to have is we want to have a B somehow, and we want to return that B. Okay, right? This is what we're trying to create here. We're trying to create IO of B. So in order to do that, we need to call ACB with an A, but we don't have an A. Well, how can we get an A? Well, we can get an A by calling CA dot unsafe run. And unless I made a typo, this actually should be it already, and it's called map actually. Whoops, it's called map, and it needs to produce just a B over here. Okay, so this is now a map, right? It looks basically the same as flatMap, but a little bit simpler, right? So it doesn't go too much, because this is basically the regular composition and not the Kleisli composition. I'm gonna say a few more things about map a bit later. I just want to go back to our full comprehension as fast as possible. What we also need to do is we need to go to our infix notation for higher kinds, and we need to duplicate that, and I'm gonna call it map over here, and it doesn't produce a CB, it produces just a B, and it does that by just calling map. Oh, and by the way, this is not ACB, this is just AB. Okay, AB like this. So let me also go to monad and say that this is just an AB. AB, now it makes sense. Okay, we're calling AB with an A, and B comes out. Okay, let's do this over here as well. Over here, AB, like this. Okay, cool. So now we can go back to our code. Right, and now I can do this map over here because it's going to compile. Okay, and now because it compiles, we actually don't need this example anymore. We can just I'm not sure if I can just do this. Did it? No, I didn't. All right, so I'm going to revert that. Let me comment the whole thing out. I'm actually not sure if we're still going to need it, but I'm just going to keep it there. Okay, so now the for comprehension should compile because now we have a map. And also now because we have a map, we don't need to use flatMap over here, right? So instead of this, we can just use an equality symbol over here, right? And we don't need to create an IO. We just have this block of code that just produces the message directly. I believe this should work. Yeah. So now we're using map instead of flatMap. So now we can also go down to the associativity law, and now I can show you that this is going to compile. Right. Obviously, again, this is pseudocode, so this equality you can ignore it. This is just like semantically that this should be the behavior of this code should be the same. Now, what a map, like a sort of hand wavy way to explain what map is doing is basically, if you had an imperative program, then you would just mash things together. And if you have a functional program, instead of mashing things together, you can just have separate functions, and you can just compose them together, and map helps you to do this. And you see it clearly over here, right? So in functional programming, this is the opposite of what you want. You don't want to mash things together. You want to compose things out of smaller things. And the cool thing about it is that even though it might be a little bit slower because you have this map and everything is being wrapped inside of this as people say burrito, then it might get slower. But because functional programming is so principled, the functional compilers, no pun intended, but like compilers in Haskell, for example, they can more aggressively optimize your code, right? Because their hands are not tied by uncontrollable side effects. They can just reason about it with so-called equational reasoning. So essentially, you write this program, and then when the compilers get better, your code gets faster, which is really cool. Now, usually this is not how you write a for comprehension. Like usually, you wouldn't have like these weird scopes. So usually, what you would do is you would just remove that, okay, and now we're just going to remove the vowels, and it's going to be exactly the same code, right? So it's exactly like this, and it's not common to have types over here, right? So we're just going to remove the ints, and we're going to remove the strings like that. There we go. Now, usually it's not even common to have assignments inside of the for comprehension. It's more common to refactor this and to put this whole thing into a separate function so that you have only Kleisli composition. Remember, the same way as we had in the point-free program, we could refactor these, and so that in the for comprehension we would only see the Kleisli composition. Okay, but I wanted it to have it like this because it's really common at this stage when you explain monads and you explain for comprehension to say, look, it looks exactly like the original problem. So if original program. So if I open the original program and let me actually do this so that I can throw it over there. Right. So if you compare this code with this code, it pretty much looks identical. And this is like the common sort of like evangelizing of functional programming. Look, it's like the same code. There's nothing complicated about it. And if you're sort of new to this whole thing and you're wondering if people are actually writing programs like this, in this style, people actually do. I actually opened, just one, but there are like many examples of like this. I just grabbed like a random library that I knew was doing something like this. And look, it's the same thing. You have a set, it produces, it's basically a Kleisli error, right? So context comes in, but the try comes out, and you have this gigantic for comprehension. The same thing here, context, for comprehension. You have list, for comprehension. You have remove, you have for comprehension. So basically everything is wrapped into this monad, right? See, look, this one is much bigger. Okay, let's go back to our code. All right, so the next thing that we're going to do is we're going to try to answer the following question. Why did the for comprehension demand that we have map implemented on monad? Isn't it like too much to ask? Like, can every monad actually implement map? And the answer is yes. See, map is usually not defined on a monad. It is usually defined on a functor. And I'm going to explain what a functor is in just a few seconds. And it turns out that every monad is also a functor because you can always implement map in terms of flatMap if you add one additional operation to the monad, which is called pure, or sometimes it's called unit. And we're going to do this right away. So the first thing that we're going to do is we're going to learn about functors. So what I'm going to do is, first of all, let me destroy the pane on the right like this. And the original program was over there now. So I'm going to go down like this. Okay, so we have our monad over here, right? This is the entire file. So I'm going to throw it on the right. So now it's over here. So what I'm going to do is I'm going to create in the functional library, I'm going to create a file called functor. So we're going to have a package fp library, and we're going to have a trait functor, and it's going to look basically exactly the same thing, like this. Okay, the objective of a functor is to lift a regular function. Right? If you have a regular function like this, it's a function that goes from A to B, then it can lift this function into another function which can take a C of A and produce a C of B, right? So this is the job of a functor. Take a regular function and lift it up. Now this is a current function, so let me save it first. Okay, so this compiles. So if you're not used to this, then Scala has a syntax for this, right? It says, okay, you can just give the first one a name, right? So you can just say, okay, that this one is AB, right? It goes from A to B. And then the second one, which is going to be, it's a current function. The second one is going to be CA, which is this one. And the whole thing is going to produce a CB. Right, so I've just written exactly the same code. And now if I duplicate this again, I comment this out, and I swap this one, like this, okay, then it essentially becomes map, right? So if you compare it, this is exactly the map that we have over here, right? I'm gonna put it down. This is exactly what we have, okay? So a functor is defined on a map. So this is what we're gonna do. We're gonna have a map over here. Now we're going to remove map from here, and we're just gonna say that every monad is also a functor of C, like this. Okay, now the code remained the same. Now, as I just said, every monad is a functor because you can implement every map in terms of flatMap if you add an additional operation. Okay, so what we can do now is we can go over here and we can say override def, and I'm just going to copy that like this. Okay, so now all we need to do is we need to produce a CB somehow. And I said we can do it with flatMap. Well, let's try. Okay, so if we just call flatMap, well, what it wants a CA. We're in luck. We have a CA. Okay, so now what it wants a function that takes an A and produces a CB, but we have a function that takes an A and produces a B. So let's just try to create this function in place. So it's going to be a function that takes an A, and now what we need to do is we need to produce a CB somehow. But how can we do this? All we can do is we can call AB with an A, but now this is a B. So now if we had another function which is called pure, right, which takes a B and it produces a C, then it produces a CB, then we're done, right? So basically we need to say, okay, the monad is actually defined not only in terms of flatMap, but it also is defined in terms of pure. So if we had a function called pure, which takes a B like this, and it can produce a CB, I'm just gonna throw an exception like this over here, just so that you see that it compiles, right? So if we had this, then we can implement a map in terms of flatMap. And also, as always, I'm gonna I'm gonna start with an A. So this is gonna be an A, and also this is going to be a by name parameter, like this. Okay, so this is going to be the pure function, and before we go and implement it, I'm also going to do the aliases, right? So pure is also sometimes called point, and it is also sometimes called unit, right? So and both of these are going to be inlined like that, and both of these they just call pure with A, just call pure with A. Okay, so now it compiles. So now we can remove this, and now what we need to do is we need to go to IO, because it's going to say, hey, IO is not a monad anymore because it doesn't implement pure. So we can just copy pure. We can go to IO, right? And we can just go over here and we can say final override, and we can just paste it in pure, and C is going to be IO. And how whoops. Press page down all of a sudden. Okay, so how can we create an IO? Well, it's basically our create method, right? So this is just create A, like this. So now we have the pure function. So pure function basically takes a regular value and wraps it into the monad that we're talking about. In our case, it's an IO, okay? And that's also why it's a by name parameter. Notice that even though a monad already implements map, IO goes ahead and implements map as well. So now I can just throw it out and it will behave exactly the same way, right? Our for comprehension still works because, our map is already implemented in terms of flatMap. But this is actually an optimization, so we're actually going to leave it over here. It's going to help us in the next video, okay? Because this is a bit more performant because it doesn't have to wrap the whole thing, with flatMap and so on. So now that we don't have map defined straight on a monad, it is instead defined on a functor. We can actually go to our package object where we have this infix notation for higher kinds, and we can relax this requirement a little bit, right? So we can say it's not only going to work for monads, it's also going to work for functors, right? Because this is what has map, right? So it's just enough if it's a functor. And also because we're in the process of creating a functional library, we can also create a summoner for functor. We're not actually going to use it, but we can actually still add it, right? So we're going to go over here. We're just going to say that all of this is a functor like this. And because these look actually exactly the same, we can actually extract it out in its own thing. In fact, I'm just gonna copy that. Okay, I'm gonna make it a trait, and I'm gonna call it summoner. I'm going to say that the summoner is defined for any D, which is in our case is going to be a functor, that is parameterized with something that is actually that it actually has its own other type. I typed it wrong. Hold on. So it's a D that doesn't just have an underscore. It has an underscore that has its own underscore, right? So it looks a bit weird, I know, but it's basically because over here we have a functor of C of A, right? Functor of C of A. So it's the same thing. So this is going to be a functor of C of A. So now everywhere where we say functor, we're just going to put a D in, and we should be done actually. Okay. So now I'm just going to go create. I'm just going to cut it out like this. And before I cut it out, I want to show you how to use it. So we can over here we can just say that this is a summoner of functor, right? So it's going to behave exactly the same way. So now I can just cut it out. Okay, and I can create another file. I can say that this is a package fp library. Now I can save it as summoner like this. Okay, so now we have the summoner, we have the functor, and now we also have the monad, which also has a summoner, extends a monad of extends a summoner of monad. Okay, like this. Bam. Okay, cool. The last thing that we're going to learn about today is why flatMap is actually called flatMap. And we're going to do this by realizing that there's a different way to define a monad. So right now, a monad is defined in terms of pure and in terms of flatMap. And map is defined in terms of flatMap. There is also a way to go another way around. So now map uses flatMap, but there's also a way to use map from flatMap. So effectively, if we're not going to override map, and if we're not going to request that a monad has a pure function, instead, we're just going to go and we're going to implement flatMap directly by using map, because now we know that monad is a functor, so there will be an implementation of map. So now we can go right away and just implement it over here, right? So now I'm just going to go over here. I'm going to say equals, and let's see what we can do. Okay, so assuming that we have a map that can take a CA, then we can call it. Right, we can give it the CA, and I'm also going to help out with the types over here, right? So map is going to work for any types A and B. So our A is obviously still our A, but I'm gonna write it over here just so that you see. But what if our B is going to be a CB? Right? So a map can do this, right? So a map can take a function from A to CB and raise it to CA to CCB. Right? So this is what a functor was doing, right? So in fact, let me actually type this out, right? So a functor takes a function from A to B, right, and converts it into a function of CA to CB. But what if our B is already a CB, right? CB. Well, no problem. Then hold up. Then it's going to convert this into a function that takes a C of A and produces a C of B. Right, it can totally do that, right? It's just gonna wrap them like this. So effectively, what it means that we can actually use this function and just pass it to map. Okay, so we can just pass. Whoops, we can use this ACB. We can just pass it to map. Okay, so the problem now is that this entire thing, right? I'm gonna do this. Right, that this entire thing is now going to produce a C of B, but what we need is a CB. So if we had another function and we're going to call it flatten, I'm going to call it flatten like this, and what flatten will do is it's going to be defined on a monad as well, obviously. Okay, it's going to be here. It's going to take some A, whatever it is, and it's going to take the CCA. We said it was B, so let's do it with B so that it's less confusing. Okay, so it's going to take this CCB, and which is of type CCB, and somehow it needs to flatten it, right? So somehow it needs to extract the inner one like this. Okay, so and now because we want to start with A always, we're going to go A, right? So now if I'm going to save it, nothing's going to compile because the IO obviously doesn't implement flatten. But let's try. So I'm going to save it. Hold up, I also need to comment these ones out, right? Because they call pure. Okay, so let's see. So in the functional library, we have two errors. One is going to be you can't implement monad because you don't implement all the methods, and also you're doing a final override on pure, but pure is actually not there anymore. So we can go over here to IO over here and say, okay, let's not implement pure. We do want to implement map, but we don't want to implement flatMap, right? So we're just going to cut it out, right? So instead, all we want to implement is flatten. So we can go over here and we can say final override def flatten, which has this type, and C is going to be IO, right? So every C is going to be IO. right? Okay, so we're just going to have equals over here. And how can we do this? Well, the sort of naive way to do this is it would be just to follow the types. As I said, this doesn't always work, right? So the compiler doesn't always help you out. So if we already have a CCA, then we can just call unsafe run on it, right? And it will just give us whatever's inside, which is an IO of A. So it should compile now, right? But obviously the code is broken, and it's the same pattern. We have to follow the same pattern. Every time we implement something inside of IO, we need to start by creating an entire IO, right? So basically we just need to create this IO.create, we need to put this inside of there, but now we need to call unsafe run twice, right? Because now it's not going to compile, right? Because it's going to say, hey, I wanted an A, but you gave me an IO of A, and you're going to say, oh yeah, sorry, I'm just going to, unwrap it again, right? So remember, calling unsafe run inside of IO is fine, right? So this is the same as we have above. In fact, let me, how are we doing this usually? Usually we're doing this. We're usually doing that. And we're saying, okay, so this is going to be a CA, right? And this is going to be an A, which is a CA.unsafe.run. And what we need to produce is A, right? So we need to produce an IO of A. So we do an IO create, and we give it in an A, right? So this is exactly the same code. Okay, so now everything works in terms of flatten and map, right? So now we need map and flatten, and before we needed pure and flatMap. And now you know why flatMap is called flatMap, because it's essentially map and then flatten, right? So it's just a projection from map to flatten. I'm also going to remove this type like this, right? So this is how flatMap can be implemented, right? Now, because we have everything, we can actually not do this. We can actually force our implementers to implement all of them. Okay, so I'm just going to remove that. I'm just going to say, oh, by the way, flatten is also sometimes called join. So I'm going to also have inline join, and it's basically flatten of CCA. Okay, so okay, let me remove this. Let me comment this one in. Okay, let's also not override the map, even though we could. Okay, so we have a monad, and it's defined in terms of pure, flatMap, flatten, and and map that is coming from the functor. And I'm also gonna bring flatMap down over here so that it makes more sense, because this is just an alias, right? So I'm just gonna put flatten down over there. Okay, right? So you can define these on any monad, right? Any monad can have a pure flatMap and flatten, right? So if I'm just gonna save this, then we're gonna go to IO, and we're gonna make sure that we're overriding all of them. Okay, all of them, right? 4 things. We have pure, we have map, we have flatten, and we have flatMap. And I'm going to bring flatten down so that we have the same order, even though it doesn't really matter. I'm going to take that, and I'm going to bring it down over there. Okay, so we have pure, map, flatMap, and flatten. And the last thing that we're going to do, we're going to go to the infix notation, and we're going to make sure that we can call flatten in the infix notation as well. So we're going to say that this is a flatten of D, and we need to make sure that there's going to be an implicit monad of C. And now what we need to produce is we need to produce a C of D. And how we're going to do this? Well, we can call m dot flatten with, hold on, if we do CA, our CA is, well, it's just a CA, but what flatten wants is a CCA. So we need to somehow prove that this CA is actually a CCA. So, and you do this by just saying, okay, I also need a view from CA to C of A. And if I have that, well, then I can just call it over here and it will compile. Okay, like this. CA, come on, like this. Okay, so this is flatten, and we're also going to have a join, right? Def join at inline def join. And also, by the way, I forgot to say that map is also sometimes called fmap because it's on the functor. So we're also going to have fmap over here, and where's our functor? We're going to have it over here as well. It's also sometimes called fmap. Line fmap, which is just map of CA and AB. Okay, so now just as a tiny proof that that this flatten thing works, because we don't actually need to create this. It's basically the Scala compiler is going to do this for us. It's going to realize that if our CA is actually nested, then it's just going to work. So what we can do is we can go to our program, for example. In fact, you know what? Let's go to our interpreter. right? And I'm just gonna real quick comment everything out, and instead of running this, I'm just gonna see that this is going to run. I'm just gonna say that this is a 5, and it's going to be io.create of 5, right? So we have a nesting over here, right? So this is an io of int, okay? And now if we have, I'm gonna call it 5io, and now if I wanted the 5, which is an integer, I can just say 5io dot flatten, and we can print out the 5. Obviously, let's see if I made any typos. I did. 5io flatten is not there. Oh, it's not complaining the flatten is not there. It's complaining that I wanted this, but you gave me that. We want to flatten, and we want to call unsafe round on it, right? So I just want to show you that flatten is actually there, but it says that it's not there. It's not there because I ruined the definition, because it doesn't need an A over here. It needs a D over here and over here, like this. Okay, now it should work. No, it doesn't work. What else did I do wrong? Oh, I just fixed only join. I forgot that I need to fix this one as well. D. Okay, there we go. So now we have the flatten, and it's obviously not going to work if this was just an IO of int, right? So if I just do this, IO of int, and we're just going to have one layer less, then it's going to say, hey, you know, I don't have the view for that thing. So it's going to say no implicit view available from IO int to IO of D, in this case, IO of int. Okay, so this is how it works. Let me comment this out again. Let me enable the, you know, our original example like that. There we go. All right, the last things that we're going to be doing is we're going to learn new words. So the same as we defined map on a monad first, and then we realized that map is actually a part of a functor, the same thing is happening to pure. Pure is actually usually defined on a thing called applicative, which is also a functor. So what we're going to do is we're going to go here, create a, I'm just going to copy that. I'm going to create a new file, going to paste it over here. I'm going to say that this is an applicative. Okay, so an applicative it just has the pure, right? So it has this, right? And an applicative is always a functor, so it extends a functor of C. Okay, so now it still compiles, right? Does it compile? Functor is already defined. What? Oh no, I just need to scroll down. There we go. Okay, so now it's all good. So now I can go over here and I can say that this is not a functor, this is actually an applicative, right? So now I can, now I don't need pure. And the same thing with a flat map. So we can actually go and we can create a flat map. I'm going to copy this, new file. I'm going to say, I'm going to call it flat map. Usually it's called bind, like in Haskell it's called bind. So now I'm just going to say that this is a flat map over here. So what we need to do is we need to cut these out, put them over here, right, like this. And now we can say that monad is just a flat map with applicative, like this. It's a flat map of C, right, like that. Save the file. There we go. Okay, so what do we have? We have the summoner, we have the functor, we have the which just brings map, we have the applicative, which is a functor which also brings pure, we have a flat map, which is a functor that that also defines flatMap, and we have a monad, which is a combination of flatMap with applicative, and it also defines flatten. So now what we can actually do is we can go to the to our syntax over here, and we can say that for these guys, it's enough to just have a flatMap like this. And the same thing for Kleisli composition, where's our point free. So in order to, you know, I said from the very beginning that you need monads for Kleisli composition. Well, in fact, it's enough if you just have a flat map. Right, so it's still gonna work. Okay, so technically it's enough to have flatmap, but flatmap is actually the essential thing of the monad. I know that this video is getting too long, but actually I forgot one thing. Because a monad is also, you know, it is also an applicative, and applicative brings pure and unit and whatever. There also needs to be laws for that. So let me actually go to the point program. So there's the associativity law. Let me actually copy that like this, right? And I'm gonna say that this is going to be the identity laws, right? There are two laws. There's left identity and there's right identity. And it basically says, okay, so if we actually have a monad, right, it's a monad of IO, then if we have a function that can take any type, right, and can produce anything that has a monad of string, for example, right, by doing a and then just calling m.pure and producing an a dot to string. Okay, so if we have that function, then if we call m.pure on that any value, right, which is our 5, if we call flatMap after that and we're passing this function f, then it should be the same as calling m.pure, passing it any value, and not doing anything at all. I ruined the whole thing because I used to the infix notation, so we actually need this pure over here. Whoops. So we need to have the IO over here. All right, so if we have this IO over here, so if you're calling m.flatMap and we're passing the IO over here, then it should be the same as basically just using IO directly. Okay, what is it not like again? flatMap, what? I gave it 2 things. Where's explicit writing flatMap, blah, blah, blah. Hold on, what's happening? We go to flatMap, it needs this and it needs that. That's exactly what I gave it. I gave it an IO of int, and I give it a function that takes it and produces IO of int, IO of string. Okay, should have worked. Oh, I'm so tired. Oh my god, it's probably because of the equal sign, right? No? Yeah, it's because of the stupid equal sign. All right, so this is the left identity like this. Okay. In fact, you know what? I'm actually going to write it with the syntax that we used to. So IO flatMap f is the same as IO. Okay, so this is what I wanted from the very beginning. And now the right identity is a bit more involved. So if we call f with any value, right, was our 5. Okay, so this is essentially IO of int, and then we call flatMap on it with a function that takes an a and does the m.pure, or let's just do IO create. It's going to be a bit more simpler to understand. IO create a, then it should also be exactly the same thing as just IO dot create any value, right? So we can go directly, so we don't have to go through flatMap. This is the definition of identity. It's basically saying it doesn't matter if you apply it from the left or from the right. Let me put it over here. This is the right identity. That it's not going to change the thing that you're applying it to. All right, so let me destroy this pane over there. So again, we have the summoner, we have the functor, we have the applicative, we have the flatMap, we have the monad, which is flatMap and applicative, and then we have the IO, which implements the entire monad, and we have the point-free compositions, and we have the infix notation syntax basically for all of this stuff. So as I already mentioned, by the end of this series, I'm going to rip out this library and put it on GitHub. Please don't use it in production. It's just for educational purposes. All right, so there's going to be only one more video about monads, at least for now, in which we will also handle the error that is coming in from wrong input, right? So because right now, if we go to our prompt Kleisli, if I actually replace this with that, okay, if I run it now, if I put in a 4, then it's going to be fine. But if I run it again and I put in some garbage, then it's going to explode. And this is what we're going to deal with in the next video. Hold up, what am I doing? All right, let's have a 5 in there again. Okay, there we go. All right, I'm sorry that this video was so long. It's been Vlad, devinside.com. Like this video if you did. Subscribe if you want to improve the developer inside you. If you find my videos valuable, consider supporting me on Patreon. And most importantly, take care.